At high level, a vector database looks like magic. You hand it a query, say a sentence turned into a list of numbers, and it hands you back the 10 closest things out of millions. And almost everyone pictures the same thing happening inside. It compares your query to every single stored vector one by one and keeps the closest ones. But let us actually think about that. Let us say we have 100 million vectors and each one is 1500 numbers long. Comparing against all of this means touching something like 600 GB of data for one search. And you want this back in a few milliseconds, right? So that brute force picture cannot be what is normally happening at scale, and it isn't. The whole reason a vector database exists is to avoid doing exactly that. And what does it actually do instead? This is the whole video about that. And here is the reframe. A vector database is not a similarity engine, it is an approximation engine. It is allowed to be wrong on purpose. And once you see it that way, every design choice, every knob, every product just falls out of one single question. Now, first and honest thing, because a lot of explanations skip it. If you only have 100,000 vectors, brute force is completely fine. Just compare against everything. Postgres does it. A plain library does it. And it is simple and exact. Below roughly a million vectors, you often do not need any of that fancy stuff. So do not add it before you need it. But let us say you keep growing 10 million, 100 million. Now that full scan is touching 50 GB of data per query, for example, and your latency, the time it takes to get your answer, just spikes up. So the obvious thought is okay, let us build an index, like a database index, that skips most of the data. And here is where it gets interesting, the classic indexes. The tree structures that make normal databases fast, they basically stop working in high dimensions. And the reason is a genuinely strange thing called the curse of dimensionality. If you think about it in two or three dimensions, some points are clearly near you and some are clearly far. But as you add more and more dimensions, something breaks. The distance to your nearest neighbor and the distance to your farthest point slowly become almost the same number. Everything is roughly equidistant. So just find the closest one stops even being a meaningful question. And the tree indexes degrade until there are no better than scanning everything. Now, I have to be careful here because this is the part people get wrong in other direction, that everything is equidistant. Result is a math idealization. It assumes every dimension is independent and random, and real embeddings are not random at all. They have structure. Think of it like this. All your embeddings are actually sitting on a crumpled sheet of paper inside a giant room, not scattered everywhere through it. They live on a much smaller shape than the space they are stored in. And honestly, that structure is the only reason any of this works. So hold both ideas at once. High dimensions are hard enough to kill the old tree indexes, but real data has enough structure that we can cheat. And cheating done properly is the next idea. So here is the deal we make, and it is the single most important idea in the whole topic. We stop asking for the exact nearest neighbors. Instead, we ask for most of them, almost all the time, and we go much faster in return. This is called approximate near neighbor search (ANN). Approximate is right there in the name. And the way we measure how good the approximation is recall. Recall just means out of the true nearest neighbors, how many did we actually find? If the real top 10 are these 10 and we found 9 of them, that is recall of 0.9, 90%. And here is the thing to hold on to for the rest of the video. That number is not fixed. It is a dial. We choose it. Because everything here is a three-way trade: recall, latency, and memory. You can have really high recall, but you pay in speed or in RAM. You can go blazing fast, but your recall drops. There is no free corner, and the entire field is just different clever ways to sit on that triangle. So, what is the first clever way? The simplest good idea is do not scan everything. Group the vectors into clusters first. Carve the space into cells, each with a center point. Now, when a query comes in, we find the few nearest cell centers and only search inside those cells. Let us say we split into 1,000 cells and probe just the closest few. We just did a tiny fraction of that work. And it works mostly. But you can already feel the crack. What if your true nearest neighbor is sitting just on the other side of the cell boundary? In a cell we did not probe, we miss it. Our recall drops. We could probe more cells to fix it, but that is a dial again. but that costs speed. So cells are good, but the hard boundaries are a real weakness, which makes you ask, what if the index had no hard boundaries at all? What if it was something you could just walk? So this is the idea behind the most important index in the vector search. It is called HNSW, and we will build up what those letters mean. Forget cells. Instead, connect each vector to a handful of its nearest neighbors, like a network of friends. Every point knows a few points close to it. This is called a proximity graph. And now searching is not scanning, it is walking. We drop the query in at some node and then we just keep doing one simple thing. Look at all my neighbors, hop to whichever one is closer to the query and repeat. We are greedily walking downhill towards the query, one step at a time. And because near things are linked to near things, we very quickly end up in the right neighborhood. That is the core move. The graph itself is the index and we navigate it. But there is a catch, and it is the reason for that extra letter. If we start walking from some random point that is far away, and every hop is only a small focal step, it takes a lot of hops to cross the whole space. It is like being dropped in a random street and having to walk to the other side of the city, one block at a time. Only ever asking the person next to you. We get there, but it is slow. So we need a way to make big jumps first, then small steps. So the fix is genuinely elegant. And if you have ever heard of a skip list, this is the same trick. We build the graph in layers. The bottom layer has every single vector densely connected. That is where the precise work happens. But then above it, we keep thin layers with fewer and fewer points and longer links. The top layer might have just a few nodes with links that span the entire space. Think of it as highways on top and small local streets at the bottom. And now the search makes those big jumps fast. We enter at the sparse top layer and take a few huge hops to get roughly close. Then we drop down a layer where the links are shorter and refine, then drop again. By the time we reach the dense bottom layer, we are already in the right area and we just do the fine grained final search there, coarse to fine. And that is the whole H, hierarchical. The full name is Hierarchical Navigable Small World. Fancy name, but you just have seen the whole idea. And the payoff, because we jump far at the top and do the detail work at the bottom, the number of steps grows roughly with the logarithm of the number of vectors, which is wild. Going from a million vectors to a billion, that is 1,000 times the data, is only something like 50% more steps. That is property that makes this thing work at scale. Now there are three knobs and it is worth knowing them by name because these are the dials you will actually touch. M. How many neighbors each node links to? More links, better recall, more memory. EF construction. How hard it works while building the graph. And the important one, EF search. How many candidates it keeps while searching. And the last one, EF search, is the recall dial we keep talking about, made real. Turn it up and the search explores more. Recall goes up and it gets slower. Turn it down, it is faster and misses more. Same index, same data. You are just choosing where to sit on the triangle at query time. So let us step back because this quietly changes the question people usually ask. They ask, is a vector database accurate or is it fast? And honestly, that is the wrong question. It is whatever you want it to be. Accuracy is not a property of the system, it is an operating point that you pick. So when a vendor tells you we do 12,000 queries a second, the honest question is at what recall, right? Because you can always make that number bigger just by turning the recall down. A throughput number with no recall next to it means almost nothing. And here is my favorite proof that recall is a choice. PG vector itself. The Postgres extension for vectors. By default, it does not approximate at all. It does an exact search, perfect recall. It is only when you add an approximate index that you start trading recall for speed on purpose with your own eyes open. So the approximation is not something the database forces on you. It is a choice you make and you should know you are making it. That is the important part. So HNSW is fast, but nothing is free. And the bill here is memory. Because to walk that graph quickly, you want the vectors and all those links sitting in the RAM. So let us do the napkin math because it is the number that decides everything. One vector at 1500 dimensions, 4 bytes each, is about 6 kilobytes times 100 million vectors, that is roughly 6 GB, times a billion, 6 terabytes. And that is before the graph links. That is a real wall, not speed, memory. So, how do we get under that wall? The first way is quantization, which is just a fancy word for store the less number precisely. We can drop each number from a 4-byte float to a single byte, that is 4 times smaller. And you often keep around 99% of the recall, that is basically free. Or we go more aggressive, product quantization. Can compress a vector by something like 64 times or all the way down to a single bit per number, 32 times smaller. And surprisingly, you can still keep the vast majority of the quality, especially if you do a quick cleanup pass at the end. So, quantization is how you trade a little recall for a huge amount of memory. And the second way is do not keep it all in RAM at all. Put the big graph on a fast SSD and keep only the compressed vectors in the memory. There is a system from Microsoft Research called DiskANN that does exactly this. A billion vectors searched on a single machine with 64 GB of RAM plus an SSD at 95% recall in under 3 milliseconds. Now, to be fair, that benchmark gives smaller vectors than a typical embedding, so do not read it as 6 terabytes squeezed into 64 GB, literally. The real takeaway is the shape of the trick. Compress the vectors into memory, push the big graph onto the SSD. Thus, that is what makes billion scale affordable. And one honest aside, because it is a fun one. Researchers recently found that for real high dimensional embeddings, that whole layered hierarchy barely even helps. You can often just drop the upper layers, keep the flat graph, and get almost the same speed for less memory. So even the centerpiece has a weight. Do we even need this part? The field is still moving. Okay, so far this all sounds clean. Now let me show you the part that quietly ruins people's weekends, filtering. Because in real life, you almost never just want the nearest vectors. You want the nearest vectors where the user is the person or the date is the month. You are combining a similarity search with a normal database filter, and that is genuinely hard. Think about why. You have got two options, and both have a problem. Option 1, filter first, keep only the matching rows, then search. But our fast search was a graph walk, and if you rip out most of the nodes, the graph is full of holes, and the walk gets stranded. Or you fall back to brute force over what is left. Option 2, search first, then filter. Do the normal fast search and throw away the ones that do not match at the end. But let us say only a tiny fraction of your data matches the filter you search. Get your 10 nearest and then 8 of them get filtered out. You are left with 2 results when you asked for 10. So neither one is clean. And this is an active research problem. There are clever newer methods, but you should know it is a real hard trade off, not a checkbox. And there is a second real world crack, and it's a good one to be honest about. Vector search is fantastic at meaning, but it is not always what you want. Let us say someone searches for an exact error code, or a product ID, or a specific name. The vector will happily return that things that are semantically in the neighborhood, kind of related. While completely missing the exact string match, good old keyword search, the thing we had for decades, nails that instantly. There is even a well known benchmark where plain keyword search beats fancy embeddings on a big chunk of real queries. So, the honest answer and what serious systems actually do is not vectors instead of keywords, it is both. Run keyword search and vector search together. That is called hybrid search and combine the results. Vectors get the meaning, keywords get the exact match. Do not throw away 40 years of search just because embeddings are exciting. So, with all of that, let us look at what the real systems actually run because now the names make sense. The honest summary is almost everyone builds on the ideas we just covered. Most of the dedicated ones, VWhite, Quadrant, Milvus, are built on HNSW. And the vector search added to classic engines like Elasticsearch uses a graph index as well. Milvus is interesting because it does not pick one for you. It lets you choose the index for your use case. Pinecone is its own proprietary thing that mixes brute force, product quantization, and cells depending on how much data is sitting in each piece. So it is the same small set of ideas, just arranged differently. But here is the question I actually want you to walk away with. Do you even need a separate dedicated vector database? Because that is not obvious. PG vector, the one we mentioned earlier, is not a separate database at all. It is just an extension to Postgres. You run one command and the database you already have does the vector search. with your existing rows, your existing filters, your existing backups. Let us say you have got under a million vectors. Your filtering matters a lot and you are already running Postgres. Honestly, you might not need a new piece of infrastructure at all. A dedicated vector database ends its place when you are at a serious scale or when you need very specific performance. But we are doing AI, so we obviously need a vector database is exactly the kind of assumption that adds a system you do not need. Match the tool to the actual numbers. So where does all of this actually live? Most of the time inside a RAG pipeline, retrieval augmented generation, which is the big phrase for a simple idea. Before the language model answers, we go and fetch the relevant documents and put them in front of it. And the vector database is fetch relevant document step. It is one stage, not the whole thing. And there is a nice pattern here that ties back to what we learned. The vector search casts a wide, cheap net. Give me 100 roughly relevant chunks, fast. That is the approximate search we built, but roughly relevant is not good enough to hand to the model. So then a second slower smarter model called a re-ranker looks at those 100 and carefully picks the best handful. Cheap and wide first, expensive and precise second. You would never run the expensive one over all of your data, only over the small candidate set, the fast one found. And if the two stage shape feels familiar, it should be. It is the exact same move as the load balancing video, where we put a fast, simple tire in front and let it hand the hard cases to a smarter, more expensive tire behind. Cheap and wide first, expensive and precise second. You never run the heavy thing over everything, only over the small set that the cheap thing already narrowed down. That one pattern shows up again and again in these systems. So we covered a lot: brute force, cells, the HNSW graph, quantization, disk, filtering, hybrid, and it would be easy to walk away with a pile of names to memorize. Do not do that. Because at high level, it all comes back to one single idea. A vector database is not a similarity engine, it is an approximation engine. It is allowed to be wrong, and the entire game is you choosing how wrong you are willing to be and where you pay for it. And where you pay is really just three places. You pay in recall, how many the true neighbors you are willing to miss. You pay in latency, how fast it has to come back. Or you pay in memory, how much RAM, and money you are willing to spend to keep it fast. HNSW, quantization, disk, cells, every one of them is just a different way of moving cost between those three. Answer where you are willing to pay, and the right choice basically picks itself. And the one line to remember the whole thing is this: you are not searching for the nearest vector, you are choosing how close is close enough. And honestly, this is what makes these systems beautiful. They get incredibly good answers at a billion scale, precisely by being a little bit wrong on purpose.